the lecture is an instant.
Okay. So let me tell you what these lectures are about, okay, before starting. Okay, in the first lecture, I will describe instantons in a notation which was used by Attia a few years ago, in which instantons are described using quaternions. Okay? This is just a way of rewriting the known solutions of Toft for winding number 1, but there are various interesting aspects of this way of rewriting things, which will then allow a generalization, okay, of these solutions. Okay? I guess so. I guess so. Something like this. And what I will say in this respect, you can find in some lectures that Attia gave to the Scuola Normale in Pisa, probably 30 years ago or so. Okay? I will go slow because the language of Attia is the language of mathematicians, so it's something that maybe physicists are not really accustomed, to discuss. Okay? Then from this construction, okay, one can go to a generalization which is called the ADHM construction of instantons. That is, you will see that in reality, mathematicians rephrase the problem of constructing instantons, which are solutions of a certain differential equation, which is a differential equation of Young-Mills, in a framework in which they construct what are called holomorphic bundles. Okay, and then we'll try to go through this step and to justify why this is so and what comes out of this construction. Then there is a third part in which we do what is called ADHM calculus. That is, once you have the solution for the gauge field of the problem what you want to see is what are the rest of the so-called zero modes of the theories. Okay, because really when you compute an integral, okay, what we are doing here, we are thinking of doing a saddle point. Okay, that is, you have to compute a certain action which is m minus SA. Okay, we imagine to do a quadratic approximation of this action, okay, with respect to the classical solution, plus what are called fluctuations, okay, and this is a certain operator that then we'll see what it is, okay, and the idea here is that these fluctuations, you have to know what is their form, okay. So what comes out is that when you have a differential equation, okay, the solution of a second order differential equation has a certain number of parameters. These parameters are to be determined from the boundary conditions of the theory, okay. This is true also for the classical field, okay. If you compute, the classical field, the Toft solution, there are a certain number of parameters. Okay, the parameters are how this object is large, what is its size, and what are the rotations. Okay, how does this object is rotated in the space of configuration. Okay, now in modern language, what these kind of parameters, which once were called collective coordinates, are called moduli. Okay, so we have to construct, the moduli space, that is to find all the parameters of this solution. In the moment in which we know what the parameters of these solutions are, we may try to perform this integral, which is a functional integral, okay? Because it's an integral over these variables, okay? Now, the ADHM calculus is nothing else than a way of writing the fields, which are solutions to the classical equation of motion, in terms of this moduli space, okay? So, we'll go through this part. There is a nice review of this subject in a review by Dorey, Koze, Mattis, and Hollowwood, which I'm not placing in the right alphabetic order. I'm sorry. Hollowwood. Okay, in which they review all of these subjects. It's a very thick review. Okay, we are just going through a small part of this. Okay, this is a physics report, I guess. Okay, so in the moment in which we will know how to construct these solutions and to deal with these solutions, we will see that you can, I will try to motivate that we can use a theorem which is called the localization theorem, okay? The localization theorem is just telling you, more or less, that the saddle point a quadratic order, because in principle you will have higher orders if you are doing expansion in order of h. Okay, this will be, there will be something like third order and so on and so forth. Okay, that just this result is an exact result. Okay, it's an exact result. I'll try to convince you that this is true. Okay, so this will be the 4 point of this lecture. Localization. Okay, and finally, I will show that once we have written things in terms of localization, that means in terms of an integral over the moduli space of the theory, what we can do is to perform another saddle point and recover the Seiberg-Witten equations. Okay, so Seiberg-Witten equations. Okay, which is the equation of a certain curve. Okay, when we will do the saddle point, I will show you that we can recover this equations. There is an interesting mathematical way of doing so, and clearly this last point was done in a paper by Okunkov. So I'm writing it wrong. And Nekrasov. Okay. Even though my derivation won't follow this paper, okay? But it's okay. The result is the same. This is just my way of understanding this subject. Okay, so this is the plan of these lectures. Okay, clearly I'm here, so if questions or problems or you would like more explanations, you can find me. My office is 110. Okay, so very good. So let's start. Okay, now you've seen that there are real numbers. Then there are complex numbers, okay? The extension of complex numbers are quaternions, okay? Real numbers clearly are real, okay? Complex numbers, they have one imaginary unit. Quaternions have 3 imaginary units, okay? So it's an extension of something that you already know. And these complex structures are called, historically, I, J, and K, okay? And the properties of this object are obvious, the obvious properties that you want to give to an imaginary unit. The square must be 1. So I squared is equal to j squared, it is equal to k squared, is equal to -1, okay? These are just imaginary units of the same type that you are accustomed with the standard I of complex analysis. The only difference is that there are 3 and not just 1. So in order to have 3 of those, these objects won't be, in order to distinguish, won't be just pure numbers, but they will be matrices. Okay? Now, a quaternion then can be written something like this. x1 plus x2 I plus x3 j plus x4 k. So I, j, and k are these units, okay? And x from 1 to 4 are just the 4 coordinates of real space, for example. You can imagine. Okay. There is a notion of complex conjugation, which is very close to the notion of complex conjugation that you have for standard complex numbers, okay? That is, we just change sign, okay? So we just change sign to all these terms. Okay? This part of the quaternion is called the imaginary part, okay? And this part is called the real part, okay? This is a standard extension of complex numbers, okay? We can define a modulus for these objects, which is like this, which is just x bar, and it is just sum like this. It's the standard sum of the square of the coordinates. Okay. Then, as you have a number x, you can ask what is x to the -1, okay? What is its inverse? The inverse of x, which is x to the -1, is simply x bar over x bar, which is the modulus, okay? Which can be written either like with this symbol, okay? And this symbol means just x bar, okay? So here there is a square, okay? So modulus of x, it is square root of x bar, and it's also equal x mu, okay? Which is the real part of the sum of the 2 quaternions, okay? And the reason why this is inverse is very simple, because you see, if you multiply by x this object, the result must be 1, which is the definition of x to the -1. In fact, if you have x bar times x, this is exactly this denominator, okay? So this is the way in which you see that this is really the inverse of this object. Okay. Needless to say, okay, that this part of the quaternion is something that you already knew, okay, because it's nothing else can be expressed in terms of the Pauli matrices, okay? So for example, what you can write is I equal to I0, 0 minus I, then this is equal to I sigma 3, then there is a j which is equal to 0, 1 minus 1, 0, which is I sigma 2, and then there is k, which is 0, I 0, and this is just I sigma 3, okay? This up to a certain point is arbitrary, okay? So you can clearly have different definitions, okay? This because I forgot to say that not only you have this property, but the property of these quaternions is also that ij is equal minus ji is equal to k, and then jk is equal to minus kj is equal to I, and then finally ki equal minus ik is equal to j. Okay, so you will see that if you give this representation, okay, in terms of these matrices, and you use the standard rules of commutation of the sigmas, this is exactly what you get. Okay, you can also write some of this stuff in a kind of complex style way, just defining x is equal to z1 plus z2j, okay, in which this z1 is equal to x1 plus x2i, and z2 is equal to x3 plus x4i. Okay, this is just a way of rewriting what I wrote here, okay? But in terms of two variables, z1 and z2, and this remembers or recalls, I mean, the notation of complex numbers, okay? Mathematicians like to say that this identifies the quaternionic space, which is this object, okay, with C2. Okay. Nothing special about it. Okay. One last thing. If we take the product of two such quaternions in this notation, we have Z1 plus Z2J and G1 plus G2J, okay? Then the outcome of this operation is just Z1, G1 minus Z2, G2 bar plus Z1, G2 plus Z2, G bar 1, J, okay? You have just to take the product, okay? The reason why there is this complex term is because when you get this term, you have Z2, J, G1, okay, which is one of the four terms, okay. Then this you rewrite like Z2, J, and then you have real part of G1 plus imaginary part of G1 times I. Okay, and then you see that when you have Ji, okay, there is this rule here, okay, and this changes the sign, and the object becomes. We can do explicitly, which is simpler to say it. So this becomes Z2. Then there is real part of G1 times J plus imaginary part of G1 J times I. Okay. J times I is I times J. Okay. And so this becomes Z2, Z1. Did I write Z1? Okay. This becomes Z2, G bar, which is what I wrote. Okay. So this is an introduction to these quaternionic numbers. We have to say also that if we have dx, dx clearly will become dx2i plus dx3j plus dx4k. and the same for dx bar, where you have minus, minus, minus in this position. Okay, so this is a crash course on quaternions, or quaternions in 10 minutes. Okay, good. Okay, now it's time to discuss the gauge field. Okay, I will show you that the gauge field A of x can be written like imaginary part of a certain function of quaternions, we'll see what it is, times the x, and this also can be written like 1/2 f of x minus dx bar f of x bar. We will do this by expression. And f will become dA plus A wedge A. And this is a formula that you know very well. Okay? So in components, this dA will be sum over mu, A mu, dx mu, df, sorry, dA, which is f. So this part of f, let me put in quotation mark, just this dA, this part of f will be this, okay, and this is clearly 1/2 sum mu and nu, d mu a nu minus d nu a mu, and this is dx mu wedge dx nu. Okay. Then the second part of f, so this part here, I don't know, like this, is just a mu. It's just a commutator, so it is a mu and nu dx mu wedge dx nu, which is just 1/2 commutator a mu a nu dx mu wedge dx nu. So all these formulas are standard, are just to set our notation, okay? And then finally, this f in terms of this equation here will just be imaginary part of df wedge dx plus f dx wedge f dx, okay? Because it is just dA, so it is this differential, okay? And then this is the commutator, okay? If you are not familiar with this notation of the wedge product, okay, the wedge product is, you can think of it like the commutator, okay? Is the antisymmetrized combination of these differentials, okay? So until now we haven't done anything, okay? In order to get convinced that you can use this form, okay, you have to perform a little exercise, which is not very hard to do. You have to take the standard form of Toft of an instanton, which, for example, I took from his paper of 1976, okay, in which there is a gauge connection times dx And then clearly, since this is a SU2 solution, okay, you multiply by the Pauli matrices. Okay? Now, this formula is just mu x nu dx mu I sigma A over x squared plus 1. I have, in its original formula here, there is a certain parameter lambda, which is the radius. I set this radius to 1, just to make things simpler. Okay? Now, this object, eta A mu nu, is an object which helps you do the homomorphism from SO4 to SO6, and it is defined in this paper by Toft. Okay? So, it is like this. Okay. Now, it is just A epsilon for mu, comma nu 1, 2, and 3. Okay. This index A is the index of the Pauli matrices. So it goes from 1 to 3. This index mu and nu, these are the indices of space-time, so they go from 1 to 4, and in the case in which they just run from 1 to 3, they're just epsilon. And then you have eta A for nu, which is equal minus delta for nu, and equal the eta A mu 4, which is the same, but with a plus sign. Okay? So now, it is a very simple exercise to rewrite in terms of quaternions, okay, these quantities. You just put the indices and you perform this. The outcome of all of this is imaginary, okay, of x bar dx x squared plus 1. So if you rewrite in terms of quaternions this object, this is what you get. Clearly, rewriting should be kind of straightforward. Okay, you have this formula for dx that I hope I have not erased. Okay, so it is just this formula here. Okay. So you just check that if you take this x that now was written there for x bar, you multiply by this dx, which is written here, what you get is exactly what you find from this definition, okay? Where instead of this eta, you just put this object. So it's just a matter of sitting down and putting the right numbers, okay? These objects are summed, so clearly this becomes I, J, K, okay, and you find that formula. It's just a little exercise in algebra. Okay. This is something like has nothing to do with this. I mean, in his work, he wanted to do this this transformation, so he needed, I mean, to have this SO6 or whatever, and this is what he found. These are just the sigma A alpha alpha dot. Okay, so these are the objects that clearly they send you from SO4, no, to SU2 times SU2. Okay, and in his case he had another kind of problem. So these are just the same parameters that perform this kind of transformation. But here you don't have this problem. Okay. And also this index A, clearly you have eta and then you have eta bar. Okay. In our case, we don't need to do that. Okay. These etas are self-dual, okay, as is showed. So, okay, until now everything is quite simple. Okay. Now let's compute F. Let's compute F using this formula, starting from this formula that I've written here. Okay, so f, it is the imaginary part of, okay, so I have to take the d of this object. Okay, so if you act first on the numerator, clearly what you get is just this. Okay, I've just acted upon this x bar. Okay, if I act twice on this, I get 0, just because this squared is 0, because it is antisymmetric, because this wedge product antisymmetrizes everything. So if you wish, you can think of these dx's like fermions, for example, Grassmann variables. Okay, then we have to we have to derive this one. Okay, so we have x bar 1 plus x squared time dx. Okay, and then we have to do a wedge a. Okay, because f, it is just dA, it is dA plus this a wedge a. So a wedge a means just taking this object twice. Okay, so this is just plus x bar dx wedge x bar dx 1 plus x squared squared. Okay, so this is it. Okay, let me do this computation. Okay, so this is just, I compute it on the side. dx. Okay, now this in reality is a kind of, well, because this has nothing to do with quaternions, because this x is just square root of x mu x mu. Okay, so if you wish, you can think of performing this computation just forgetting about quaternions and just doing the derivative of square root of x mu x mu. Okay, at the same time, this quantity x mu I have told you, which is the real part of the product of two quaternions. Okay, so you can write it as the real part of the product of two quaternions, and so this becomes x bar, okay, minus clearly 1 plus x squared, everything is squared, okay, then wedge dx, and here you can write dx times x bar plus x dx bar, which is the real part of the quaternion. If you want to write it in another way, you write it like this. X mu dx mu is exactly the same thing, okay? Because this comes from the derivative of square root of x mu, okay? I prefer to write it as the real part of a quaternion. Okay. Clearly, I was missing parentheses. Okay? Okay, now this is simple, becomes minus x bar dx times x bar 1 plus x squared times squared, okay? And this one is just x bar x, so it's minus x bar x dx bar wedge dx 1 plus modulus squared. Okay, so this is it. Now that we have performed this computation, you see that this part cancels this part. Okay? And so the final result is so the winner is the winner of is just imaginary part of dx bar wedge dx 1 plus x squared minus x bar x dx bar wedge dx 1 plus x squared. Okay. So you see that this part is common, so let me take it out. Dx bar wedge dx. Okay. And then we do the common denominator. Okay. 1 plus x squared. So this becomes 1 plus x squared minus x squared cancels, okay, and this is the final result. Okay? So this is our f, and this object here, dx bar wedge dx, is anti-self-dual. Okay? So this gauge, this field strength is such that star f is minus f. Okay? Actually, okay. Let's not confuse all of this. Okay. And we'll write it in component later on. Okay, so this is what we need to know for the moment. Now, from the point of view of physics, you know that for x large, okay, the gauge connection becomes a pure gauge. Okay, so in the limit in which x goes to infinity, okay, this a of x just becomes this part, since this one is negligible with respect to x squared. Okay, so in the large n limit, in the large x limit, okay, this becomes imaginary of x bar over x squared dx, okay, which can also be written like x minus 1 dx, okay, like this, and this becomes omega minus 1 d omega, okay, where omega is just x over modulus of x. Okay, this is just a gauge transformation. Okay, so a mu becomes pure gauge in the limit of x going to infinity. And this is something like 1 should have known. If we want to get convinced of this fact, we just perform the computation and we just perform omega minus 1 d omega as a check. Okay? So omegas minus 1 is just, so omegas minus 1 d omega. Let's do the check that we really find this quantity. Okay? So omegas minus 1 is just this thing, x bar over modulus of x. Okay? Now we have to take the d omega, which is d of this. So we'll have dx plus modulus of x minus, we have to take the derivative of 1 over square root of x mu, okay? And if we do so, this becomes minus x 2 times x squared, then x mu dx mu over modulus of x. Okay, this is just the derivative of this d omega. Okay, first part and the second part. This is the second part in which you take x bar and then you derive by this quantity. Okay, good. Now, this can be rewritten like x bar dx over x squared minus 1 over 2 x squared. And this one can be written as the real part, which is just x bar dx plus x dx bar. Okay? Okay. So, if you do that, this becomes just, I need to cancel. Now, if you put this together, there is this 1 over 2. This becomes just 1 over 2. This part, x bar dx, changes sign, because this is minus 1/2, this is plus 1. Okay, and so you get the real part. So this is just imaginary part, as I've written, of x bar dx over x squared. Okay? Okay, so we have just checked that in reality this a of x can be rewritten like this, and this is just pure gauge. Now we have to check another property of the gauge connection. Okay? We have found what is a gauge transformation. Okay? Now, in the case in which you are on the unit sphere, that is modulus of x is equal to 1, then this map, x, which goes to x bar, which it is x to the minus 1, okay, is a map which has degree minus 1, okay? This map means that you are sending a sphere into a sphere, but the first sphere has a certain orientation, and the second sphere has the opposite orientation. And this is why the degree of this map is minus 1, because the degree of the map is just the mapping of the domain, of 1 on one side into the range of the other side. Okay, how many times you wind around the range starting from the domain. Okay, so in this case the degree is just 1. Okay, And what we want to find is what happens when we are sending x to a minus 1. This is similar to sending the complex coordinate z in 1 over z, which you know it is a kind of transformation that sends 0 to infinity. Okay, and this is exactly what happens. You have to think that this solution is a solution on a sphere, so there is a north pole and a south pole. Okay, so what this map is telling us is what happens when we go from one chart to the other chart. No, when we go to the north pole to the south pole. Okay, what happens to the gauge field? Okay, this is clearly a gauge transformation, and as any gauge transformation, we write it like this: x bar dx over 1 plus x squared. With my watch, I mean, I have to. I need a real watch. Okay. Oh, there is a clock there. Okay. Oh, 45 minutes. Good. So you have this one, then omega minus 1 plus omega d omega minus 1. I'm just writing a gauge transformation. I want to see what happens when I go from the first chart, which is the north pole, okay, to the second chart. Okay, what happens to this gauge field? I want to understand what are the properties of this object. Okay, this is the last exercise. Then we'll start talking about new things, but we need them to do this. So this is just x bar dx over 1 plus x squared, x minus 1, plus this is x dx minus 1. Okay? So this is what we have to write. So let's perform this computation. Okay. So this is simple. This becomes x squared dx times x minus 1 plus x squared. Okay, plus x dx minus 1. This is just multiplication, so it should be pretty easy. So we write x squared dx x bar over modulus of x squared, which is just the inverse of x, 1 plus x squared plus x dx bar over modulus squared. Okay, so I've just rewritten, not acted. Okay, just going slowly. Okay, so let's perform these derivatives. Okay, so this is the x bar, just because the x bar, and this modulus cancels with the other one. So 1 plus x squared. Okay, then we have x dx bar over modulus when this d is acting upon only this x bar. Okay, then this d is acting also on the denominator. Okay, and so this is the computation we have just done. Okay, so this is the result. dx times x bar plus x dx bar. Okay, like I did in the past, I'm rewriting the derivative of this object, which is real, in terms of a real computation of quaternions. Okay? So this probably I'm missing a bar here, okay, because it is just this derivative. Okay. Okay, now you see that this x dx bar cancels with this x dx bar here. And so the final result is dx times x bar, which is this piece here and this piece here, which I can take out because all of the rest are real numbers, so they are not matrices. Okay, and you have 1 plus x squared minus 1 over x squared. Okay, so x squared cancels with x squared, and this becomes dx times x bar 1 plus modulus of x squared. Okay, with a minus sign. Okay, you see that with respect to the starting point, we have changed the x bar dx with dx x bar. Okay, so we have just changed orientation. Okay, in fact, if you now okay, now if we go to this variable x to another variable that we call y, which is just y is equal to x minus 1, okay, we want to see that in the new variable y, this is exactly of the same form we had before. Okay, it cannot change. Okay, and this is what happens. So if y is x to the minus 1, which we also write like this, okay, we have y to the minus 1, which is y bar, which is x, no? Just because x and y exchange the role, okay? And if you do the dy, this becomes just dx over modulus of x squared minus x bar modulus of x to the 4th power x dx bar plus x bar dx. This is something we have already seen. Okay, once again you see that there is a simplification. Okay, this is dx bar because I was missing a bar. Okay, because it was the dy, so dy of x bar, so I was missing a bar. Okay, so once again this cancels with this. Okay, and the final result is okay. Also here, this is dx x bar. Yes, because I have derived them in here in this order. Clearly, these objects do not commute. Okay, so you have to watch out to what is the order. Okay, so I said that this cancel this term. Okay, and the final result is x bar dx x bar over x to the 4th. Okay, good. So if now I substitute these results inside this, okay, it is convenient to let me rewrite this object in this way. X bar dx x bar, like this, 1 plus x bar squared. Okay. I haven't done anything. I've just written exactly the same thing. Okay. There is a minus, sure. There is a minus. Yes, there is a minus. Thank you. There is this minus which I missed. Okay? The way in which the reason why I'm rewriting this in this form is because I want to show this kind of pattern. Okay, so it will be easy now to rewrite this object like x dy 1 plus x squared. Okay. Once again, this can be written like x over modulus of x squared, and then like this. Okay. What I've done is just taken out x squared out of here. Okay. So you have 1 over x squared here, and then you have an x squared which I've put here. Just trying to rewrite this in order to use this formula. Okay, and so this one now becomes simply y bar dy 1 plus modulus of y squared. So what I've showed is that I recover exactly this formula. Okay, if I write instead of x, I write y, that is the exact formula. The form of a mu is not changed, okay, by this gauge transformation. Okay? This, if you put this result in terms of this variable x here, okay, you get instead, a different form of a mu, which is called the Taylor gauge. That is a form which is valid around the point at infinity. It's not valid around 0, clearly. Okay, just this is the reason why we have changed this map, from North Pole to South Pole. Okay, just because in the North Pole, we have a certain value for infinity, and the South Pole we have a different one. Okay, so if I do this, okay, and I write a of x is equal imaginary of, I'm rewriting the form from up there, okay, 1 plus x squared, okay, and now I want to write this quantity in terms of x minus 1, okay, so first step I write m imaginary part of x dx. So I've done nothing. I've just written this. Then once again, I insert 1 in this form. Okay, this is just 1. So I haven't changed anything. Okay. And then 1 plus x squared. Okay. Now this becomes imaginary part of x bar dx x bar x times, here I take x squared out, so this become modulus to the 4th, and this become like this. Okay. And then in terms of this y, of this coordinate y, what I get is minus imaginary part of dy times y bar over 1 plus y squared modulus of y squared. Okay? So you see that there is a singularity for y going to 0. Okay? So this is what is called the singular gauge, okay, of a mu. And this is the end of this part of review, okay, of sentence. Now we go to a part which is probably less known. Okay, so I have to erase something. Okay. Now, I remind you that the equation f equal star f is conformal invariant. You know that f mu is conformal invariant. Okay? Now, the conformal group in this formalism that I have written, okay, is just SL to H, okay? Well, plus or minus 1 is not important, okay? That is, if you express the conformal group in terms of quaternion, this is just the usual fractional transformation of SL to C, but where the complex numbers are replaced by quaternions, okay? So, for example, if you send in AX times all of these are quaternions, that is, this is a matrix. So now when you have to act on this matrix, okay, you have to act with the elements of SL to H. Okay? So if this in general is of this form, okay, these are the transformations that we are doing. According to which transformation you're taking, okay, you get one result or another. For example, no, like this, so on and so forth. Okay, so this, for example, is a rotation by XO4 of X. Okay. Then there are the inversions that we have already seen, because is X goes to X minus Y. Okay. And now the thing that we are asking ourselves is when I apply these transformations, what happens to the gauge field? Okay. So the gauge field is going to transform under this transformation is going to stay the same. What's happening? Okay. Okay. Now it is clearly simpler to write rather than the elements of the conformal group the transformations in this form, but there is a drawback. Okay. This transformation that I've written here is a transformation of SL to C. Okay. And it is clear what is the numerator and the denominator. But when the objects like A, B, C, D become matrices, okay, we have to pay attention to the fact if this denominator is acting from the left or is acting from the right. We have to take them in two different positions. So there will be two transformations. One, let's call it X, S, in which X goes in AX plus B. And then we have CX plus D minus 1. And so there is an action from the right. And then there is another transformation, which I call T, in which X is acted by gamma plus delta minus 1. And then I have X alpha plus beta. I've changed the names of this A, B, C, D. Okay? Now, I want to show that if you take a Quaternion conjugation, okay, what Quaternion conjugation does is to exchange this S and T. Okay? So if you want to go from one way of looking at things to the other, all you have to do is to take this Quaternion conjugation. Okay? So what I'm showing is that if this alpha, beta, gamma, and delta, okay, are just A bar, B bar, C bar, D bar, okay, and then if X, this is C, stands for conjugation, so it's the operator that makes this conjugation, then we have that it's true that T is C S C. Okay? So the relation between this S and T, these two transformation, is mediated by this conjugation operator. Okay? Let me show you that this is the case. So I have Tx. Okay? I'm acting with T on X. Okay? So this means writing X gamma plus delta minus 1, X alpha plus beta. Don't forget that there is this relation here. Okay? And this is CSC according to what I have defined before. Okay? So this becomes C S X bar. No? Because the first C on X just gives X bar. Okay? Now, in turn, this becomes C, and then we have Sx. So we take S from up there, okay? And so it will be Ax bar. We just rewrite that equation, okay, where we replace X with X bar. Okay? I'm not doing anything special. Okay? Now I apply once again C, which is the conjugation. Okay? So this means C bar X plus D bar to the minus 1. And then it is x a bar plus b bar. Okay? I've just done the conjugation. Okay? And then you recognize the equation that I've written up there, where gamma and delta are c bar and d bar, and alpha and beta are just a bar and b bar. Okay? You have to see in this equation exactly what I've called T with this position here. Okay? So this proves, what I've just written. Now, we already have seen before that A mu is preserved by the inversion, okay? Because the inversion sends x in x minus 1, which I've called y, and I've showed you just before that in terms of y's, A mu does not change its form, okay? Then, you can check, it's not particularly hard, that if you send x in ax, okay, with norm of A is equal to 1, and if you have x xa, okay, the transformations are unchanged. In fact, what you can get convinced if you have x bar dx 1 plus x squared a mu, and if I apply x which goes in ax, what you get is modulus of a squared imaginary of x bar dx 1 plus x squared. Okay, so if modulus of a is equal to 1, okay, this does not change the original field. And if you write imaginary of x bar dx 1 plus x squared, x which goes xa, now a is acting from the right instead of acting from the left, this goes in imaginary of a bar x dx, x bar dx 1 plus x squared modulus of a squared times a, which is a constant gauge transformation. Okay? So we have seen that these two transformations do not change the field A mu. So now we want to understand in general what happens. Okay? So in general, we can tell that A mu is invariant under a group 5, okay, which can be written like SP2, okay, mod plus or minus 1. Okay? This is the subgroup of SP2, which leaves, the norm invariance. Okay? So, the transformations which change the instanton, okay, are just SL to H, the coset over SP2. Okay? So, what we are doing is this. You have a gauge field which is called A mu, okay, and I apply transformations to this gauge field A mu, okay, and I want to understand what are the transformations that change the field, okay, and to separate them from the transformation which leaves the field unchanged, okay, because now we want to construct what is called the moduli space. So we want to know what are the perturbations that send, the field into another field, or the perturbations that leave the fields unchanged. Okay? Now, the elements of this coset, okay, are the transformations of the type mu x minus b, like this. You see, these are transformations of the type of this type here, okay? Are just some transformations of this type. So these transformations here are the transformations which send the field into something which is not the same, okay? So this is, mu is real, so mu is real, okay? While B is clearly a quaternion. Okay. What are the parameters of these transformations? There are 5. Okay? 4 are given by the components of this quaternion, which is the center, and 1 is given by this object, which is real. Okay? This is the moduli space for winding number 1 of the 't instanton. That is, the 't instanton has 5 parameters. Okay? Good. If we look at the gauge connection, which was we found before, which is of this form, okay? Under this type of transformation, this is what we get. 1 plus mu squared x minus b modulus squared. No, because we send x in this quantity. This is a constant, so dx does not count. So dx becomes mu x. There are 2 x's, so there is a mu squared. And here we send this in x minus b modulus with this mu squared. So this is what happens. And you see that if you stay around the center and this object can be neglected, what you get is dx bar wedge dx, which is just the self-dual combination of dx, which we have already seen before, okay, as being as having anti-self-dual properties. Okay, now that we have understood all of this, we ask ourselves how to generalize this, okay? The solution of Toft is a solution of winding number 1, okay? If we want, now, a solution of arbitrary winding number, how can we change this pattern in order to do this, okay? Then the answer is not very complicated in the moment in which we have said all of this, okay? Until now, we have used single quaternions, okay? Now we have to define objects in a space of quaternions of k dimension, where k is the winding number, okay? And this quantity, which is x, no? We have seen that a mu is x bar dx 1 plus x, and this was a single quaternion, okay? Now can be rewritten like a of u, where instead of x, we put this new quantity u bar du 1 plus modulus of u bar, okay? Where this u is just a vector, is a vector in this space. So u belongs to this space, and it is just a vector with k components, okay? So this is the most straightforward way in which we can enlarge our solution, okay? Okay, this U must be taken of the form that we have just found before, which is lambda b minus 1 bar, okay, which is just the form of these transformations that I have written here, okay, which just change the instanton in and give you a different solution. Okay, so if we do all of this, okay, we have a generalization of this construction which is subject to certain kind of constraints. The first constraint is this one. It is b bar b plus lambda bar lambda, okay, which has generalization of this quantity here, okay. Lambda now becomes a vector of k elements, k real elements. B becomes a matrix, which is a matrix of k times k objects. Okay? So we want this object to be a real k by k matrix. Okay? The second condition is that given a certain vector which belongs to h to the k, then b minus x psi is equal to 0, okay, and lambda psi equal to 0 means psi equal to 0, okay. This condition is just telling you that this matrix B cannot be reduced, okay. That is, no, you cannot out of a k by k matrix, okay, take, let's say, a piece which is k minus n, okay. So as maximal rank. Okay, this is just the condition. It is maximal rank. I mean, this k by k matrix cannot be reduced. Okay, and also this. Now you see, lambda psi equal to 0 means psi equal to 0 is the standard standard solution. If you have a times b equal to 0, then the solution is either b equal to 0 or a equal to 0. So this is just telling you that also this lambda, okay, cannot be reduced in any way. So these are just two simple conditions. Okay. And everything can be packed into a larger matrix of this form, for example. Okay? That is, you have here a certain lambda, okay? And then you have this b minus x. You can pack everything in one large matrix. Okay? Now, here comes, I will start this part, which is a more mathematical oriented part. Okay? Let's see. Okay? Let me recall what is the notion of a vector bundle. Okay? Now, a vector bundle E over X, okay, is a family of vector spaces E of X for each X belonging to X. Okay? Definition means very simple. Okay? Let's say this is your manifold. Okay? You have certain points here. EX is one of these points. Okay? And on top of this X, I put a space, which I call E of X. Okay? Now, there are special cases. For example, if X is an n-dimensional manifold, then there is the tangent space, okay, of this manifold, which is also dimensional. Okay, so in such a way that E of X is just R to the n. Okay? Now comes a part which we have to watch out a little bit. Okay? Now, let's take one of these space, which is n-dimensional with n lowercase, and embed it in a bundle, okay, which is Rn, where this capital N is larger than this lowercase n. Okay? So what we are doing now, we are taking these spaces and we are embedding everything into this. Okay? So, for example, so the tangent spaces are embedded into this R of n. What is the idea here? The idea is quite simple. Let's say that you have a certain space, okay, in which you have a constraint, okay? Like, for example, maybe you have seen in classical mechanics, okay? Clearly, if you take the Lagrangian and you substitute the constraint, everything gets messy, because clearly the constraint makes the equation much less transparent. But before imposing the constraint, okay, the situation is quite simple, or at least it's simpler than it was before. Okay, and this is what we are imagining now. There is a space in which there are no constraints. Okay, in this space, the derivative is very simple. It's just d mu of a certain function which acts on this space. Now, what happens if we project, okay, on a lower dimensional space? Okay? So, if we apply a projection, the result of this operation is a covariant derivative. Okay? It is the action of projecting, okay, from the n-dimensional space to the lowercase dimensional space that generates the connection. Okay? And this is the trick that I'm using here. Okay? Okay. This mu is just x. Okay? There are two different things. One thing are the points x's, and the other thing are these spaces. Okay? So, in the language of mathematician, okay, what you do is choosing a gauge for the bundle. Okay? Quindi, so I write choosing a gauge for the bundle E, and this gauge is nothing else than a certain map, U of x, which is just sending you from Rn to Rn like this, okay? So this U of x is nothing else than a matrix, which is n by n matrix, okay? Okay, so this is what I mean. It is to choose a gauge. Choosing a gauge just means choosing a certain function that is sending you from the lower dimensional space to the higher dimensional space. Okay. I have 52 seconds, okay, which I can use to introduce the projection. Okay, so there is this bundle. There is this this gauge. Now I can imagine to introduce an orthogonal projection to x. That is, I want to construct an object which is a projector like this one. It is exactly the same thing, which projects, okay, onto E of x. Takes any function which lives in this higher dimensional space and projects it on this E of x. Okay? So This function is given by u bar, which is a map from Rn to Rn, and has the property that u bar u is equal to 1. And you see why this is a projector, because if you take u bar and you act on u, okay, u bar u is 1, okay, and so you have p of u equal u, which is the definition, okay, of a projector, which at the same time is p squared is equal to 1, because you see that if you have u bar and you act u bar, this is still 1, so you have p squared equal p, okay, which is the property of the projector, okay. So what I've done here, I've just constructed, this projector, and I will show you now, next time, that means tomorrow, quite sharp, okay, and I will show you tomorrow what is the form of this connection, okay. The form of this connection in terms of these objects will be the beginning of next lecture. Okay, so this is it for today.
Let me start from questions. So you denoted your transformations as S and T, and does this have anything to do with standard S and T generators of SL2? So it's just a choice.
I could have used A and B, okay. Nothing would have changed.
Okay,